Okay, so 9.3, we're going to do the hypothesis test for when sigma is unknown. So when the population standard deviation is unknown, so we're going to be given a standard deviation within a sample size. Okay, so we have here when the population standard deviation is not known, we use a t distribution. Okay, so let's go ahead and underline that. We're using a t distribution, just as we did when constructing confidence intervals when sigma was not known. So same thing we did in 8.3 with confidence intervals. Okay, here we use a sample standard deviation to estimate a population standard deviation. Just as with confidence intervals, our estimate for sigma is going to be the standard deviation of the sample over the square root of the sample size. Okay, so let's show just the rejection regions first of what we would do here. So if we did a two-tailed test with an alpha of 0.02, you need to divide that into two tails of your normal distribution curve. So we're going to divide 0.02 by 2, which should be 0.01. Oh, hold on. There we go. So 0.01 on either side of our tail. Okay, so we're going to have 0.01 on either side of the tail, and we need the z value, or sorry, we do not need the z value. We need a t value for that. We need a sample size in order to get a t value, and I did not give you guys a sample size, so let me give you a sample size. Let's do a sample size of 20 for each of these. Okay, so you can't find the t value without a sample size. Okay, so we're going to go back to our formula sheet where we have our t values. Let me go ahead and pull that up for you. Or if you have your t formula sheet, pull that up. We're going to go to degrees of freedom of 19. Get it pulled up here. One second. All right, formula sheet. There it is. Okay, so all the way in the back, we have our t distribution. So we have a degrees of freedom of 19 and minus 1. So this row right here, and we have an alpha area in the right tail would be 0.01. So it's going to be this row right here. So we're going to do a 2.539 as our t value. Okay, since it's on either side of our mean, you're going to have a negative 2.539 and a positive 2.539. Okay, and then I'm going to draw my rejection region on either side of the tail in red. So if I go through this and I get a critical value, okay, with the rest of our information that falls within either one of these rejection regions, then I would reject. So this would be a reject. This would be a reject. Meaning if I get like a -3, I would reject, or if I got like a +3, or anything smaller than -2.539 or larger than 2.539. And if I get something in between those values, then I would fail to reject. Okay, for B, let's go ahead and do a left tail test. I'm going to change these a little bit. I'm going to do a significance level of 0.001 and a sample size, again, of 20. Okay, so this is a left tail test, which means in the left of the tail, I'm going to have a 0.001. Okay, and I want to find that t value associated with it. So I'm going to pull up that t chart. And I still have degrees of freedom, 19. And now I have a 0.001 in the tail. So that is 3.579 for that value right there. So very last column here. Now the thing about it though is it's on the left side of my mean, which means it's a negative value. So it's going to just be a negative 3.579. And then my rejection region would be any critical value that is less than negative 3.579. So this would be reject. And then fail to reject inside here. I just draw a smiley face. And then for the very last one, let's do a significance level of, we'll go ahead with 0.025 for a right-tailed test. And we'll do a sample size, we'll do a sample size of 15 here. Okay, so we have our 0.025 inside here. Okay, we want the t value. So our degrees of freedom would be 15 minus 1, so 14. So this curve here, and then 0.025 is going to give us 2.145. Okay, so we have a t value of 2.145, which means that any value greater than 2.145 we would reject. And then any value less than 2.145 we would fail to reject. Okay, so let's go ahead and do a problem. And that problem, I had the wording of it typed up in a different thing, but I guess I lost it. So give me 1 second. Let me see if I can pull it up. All right, so the problem we're doing, we have, according to the analysis of Federal Reserve statistics and other government data, American households with credit card debts owed an average of $15,706 on their credit cards in August 2015. A recent random sample of 500 American households with credit card debts produced a mean credit card debt of $16,377 with a standard deviation of 3,800. Notice that you're given a mean and standard deviation inside the sample. Okay, do these data provide a significant evidence at a 1% significance level to conclude that the current mean credit card debt of American households with credit card debt is higher than 15,706. Use both the p-value and the critical value approach. So the question is, okay, you have a mean of 15,706. That is the null hypothesis. Okay, the alternative hypothesis is this question right here. Okay, do these data provide significant evidence, blah, 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 to conclude that it is higher than 15,706, so greater than. Okay, so when we put this information into our test, I'm going to start with the null and the alternative. Okay, you have a null hypothesis that the mean credit card debt is equal to $15,706. The alternative is asking, is the mean greater than, okay, or greater than or equal to 15,706. So this is a right-tailed test. Okay, so we determine what type of test we want to run first. Okay, then let's pull the information. So we had a mean of 15,706. Sample size was 500. Within that sample, we were given a mean, so an X bar of 16,377 and a standard deviation of 3,800. Significance level was 0.01. Okay, so first thing we're going to do, and this has gone on to 2 pages, so we'll have to draw down at the bottom here, but we have to find the critical value of the test statistic. So we want to find a t First of all, because we're in that section, but because we were given a sample mean and standard deviation. We don't know what the population standard deviation is. Okay, so for our test statistic, we're doing a right-tailed test. So I'm just going to draw a quick model right here. Okay, my right-tailed test, I'll have a significance level of 0.01. My degrees of freedom here is n minus 1. Okay, so df 500 minus 1 is 499. And when I look that up, I do not think that it goes that high. So we go all the way to the end here. You're just going to use the infinity here. Okay, so use the infinity value to find the t-value with the degrees of freedom, and then a significance level of 0.01. So that is going to be this row right here, 1, 2, 3, 4. The fourth row, all the way at the bottom, 2.326. So that's going to be our critical value. So that's going to be right here, 2.326. All right, so we will reject, since it's a right-tailed test, if we get a t-value, when we do this, that is greater than 2.326, because that will be our rejection region. Okay, so I'm going to go ahead and I'm going to draw it on the next page for us, so we have it there. So we've got a t of 2.326. This has an area under the curve of 0.01. And I'm going to draw my rejection region in the red. And then my fail to reject, I'm just going to put a smiley face. Okay, now let's go back and we'll do the math. So we want to calculate the test statistic for this, which means we need to find the t or the z value associated with this. So the formula that we want to use, okay, is going to be x bar minus our mean over the standard deviation of x bar. Okay, now the standard deviation of x bar is going to be given to us by standard deviation over the square root of our sample size. So we need to find that first. So the standard deviation of our sample was given to us as 3,800. Our sample size is 500, so square root of 500. So 3,800 over the square root of 500 is 169, and let's do 4 decimal places. 169.9412. Okay, so then let's go ahead and plug this in and find our critical value for our test statistic. So our x bar was 16,377. Our mean, so minus the mean of 15,706. And then over this sample standard deviation of 169.9412. So let's get that value. So we have 16,377 minus 15,706 divided by 169.9412. So it's going to give us 3.9484. 9484, yeah. Okay, so that is the value of our test statistic, 3.9484. So if we just look at this real quick, if it's greater than 2.326, we reject. So let's go ahead and put that on the graph. See this? There we go. Okay, so 3.9484 is greater than 2.326. I'll put that over here, which means we will reject the null. Okay, which means we have reason to believe that the mean credit card debt of Americans is greater than $15,706. Okay, that's all you're saying there. Okay, you have reason, you're not saying it is, but you have reason to believe it is based on this test. Okay, that is the critical value approach. So the p-value approach with this one is you are going to find, okay, the probability of this value right here, 3.9484. So let me change colors here. All right, so p-value. Okay, you need to find the significance level here, or the area under this curve here. So it's going to be pretty small. Okay, if you look at this curve, there's not much left right here. Okay, for the p-value with a t is going to be this right here. So you're going to go T CDF in our calculator. I'll pull that up in just a second. You're going to do the lower limit. So remember, with normal CDF, you just do lower upper, okay? But with the T CDF, you also have to do the degrees of freedom. Okay, so degrees lower, upper, and then degrees of freedom. So on the right tail, the lower limit would be 3.9484. The upper would be a positive 99, and then your degrees of freedom would be whatever's given to us here, which was 500 minus 1, so 499. So you go second distribution. TCDF for me is number 5. And then if you have the 84, it's going to pull up lower, upper, and you enter those in. Okay, so for me, it is 3.9484, comma, 99, comma, 499 for my degrees of freedom. Okay, so you would enter all of those on the 84 and then click paste, and then you should get this value here. So this is basically 0. So it is 4 zeros and then a 4. 0.00004. Okay, so that is my p-value. You compare that to your alpha, which is 0.01. So we say, okay, 0.00004, 0.01 is less. It is less than 0.01. If p is less than alpha, you reject. If p is greater than alpha, fail to reject. All right, and that is 9.3.